All right, today we're going to start our second unit, and this is reasoning and introduction to proof. We're going to start with reasoning, and what we're going to specifically talk about today are what we call conditional statements and converses to those conditional statements. So a conditional statement, sometimes it's called an if-then statement, always comes in the format. You'll say if, and then there's a condition, then I'll have comma, then this will happen. So that's called the conditional statement. The hypothesis is the wording that follows the word if. So just the wording, not including the word if. The conclusion of a conditional statement is the wording that follows the word then. So we're just going to practice this real quick, and I'm actually not going to spend too much time working on this. So, hypothesis is just the beginning part of the sentence after the word if. So for this first one, I'm going to write it out. Going forward, I'll just have you guys circle this stuff. So it says identify the hypothesis and conclusion of the conditional statement. This says if two lines are parallel, then the lines are coplanar. If you guys remember from our first unit, if lines are parallel, they do have to be in the same plane. So the hypothesis here is the wording that follows the word if. So this would be two lines are parallel, and I'm just going to use that symbol to abbreviate parallel. The conclusion does not include the word then, but the words following that, and that's going to be the lines are coplanar, meaning they're in the same plane. All right, now what we're going to do in example 2 here is we're going to take a statement and we're going to turn it into a conditional statement. There's a couple ways you could do this correctly. We could turn them around, so we're going to talk about that real quick. This just says an acute angle measures less than 90 degrees. So we're basically just changing the wording here to make this a condition. So I just usually try to start with the beginning part of the sentence as my hypothesis. You have to start with the word if. So I'm just going to say if an angle, and I'm going to use that symbol to abbreviate, measures less than 90, and then I'm going to write the conclusion, then the angle is acute. Now, based on the statement they gave us, they didn't say a particular order we needed to write our conditional, so if you were thinking about writing if an angle is acute, then the angle measures less than 90, that would also be correct. So there's a couple ways you can do both of these problems we're looking at in example 2. So second practice question here, an integer. Integer is a nice number. It can be positive, it can be negative, no fractions, no decimals. That's what an integer is, just nice numbers. That ends with 0 is then divisible by 5. So we're going to turn this into a conditional statement. I'm going to say if an integer ends with 0, then it's divisible by 5. So the hypothesis, an integer ends with 0, the conclusion, it's divisible by 5. We're turning it into a conditional statement. The beginning part is the condition. If this happens, then this happens. Now, we're going to talk about this right now. These statements are not always necessarily true. We can write these sentences all that we want. And so we come into play here with the truth value. This is just, is the statement actually true or false? All right, so do you believe this is a true statement you're making, or is it false? If it's false, then what we do to indicate that is give a counterexample. A counterexample, and you only need one, so I'm going to write any one, doesn't have to be multiple examples, any one example that proves a statement is false. And we're going to get into that in the next example. But like I said, if you have a statement and you don't believe it's true, you only have to provide one counterexample to show that it's false. So we're going to slide up and do that in example 3. Okay, so I'm going to read this question here real quick. This says if x squared is greater than 0. So what that really means is this is going to be a positive number if I'm strictly greater than 0. So if x squared is positive, then x had to be positive. Okay, so if you can think of a number that when you square it, it would be positive, but the original number was not, that would be a counterexample. So normally we'd do this together in class, but since we got a video today, you could actually tell me any negative number. So here, if x was equal to -5, well, -5 squared, any negative number squared becomes positive. -5 times -5 is positive 25. So that meets the condition because x squared is a positive number. But this proves this statement false because I said x was -5 and that is not a positive number. So any negative number here would be an example to prove this statement false. So I would say this is a false statement here. This says if a number is divisible by 2, the number will also be divisible by 4. So the condition is the number is divisible by 2, then it's automatically divisible by 4. So to get a counterexample here, you want to think of a number that's divisible by 2, because that meets the condition, but not divisible by 4. Just like the last problem, lots of different examples here. You actually only need to come up with one. But for example, 6 is divisible by 2, but 4 doesn't divide evenly into it. 10 is divisible by 2, but 4 doesn't divide evenly into it. You could use negative numbers. You could do -2 would be an example. I'm sorry, counterexample. -2 is divisible by 2. That would be equal to -1. It would not be divisible by 4. So lots of different options for this question. A little tricky here if you don't know what the symbol means. This is an absolute value. And an absolute value makes anything you're going to plug into that positive. Now, these are written in a certain way. So the number has to meet the beginning part or the hypothesis, the condition of the conditional statement, and then this is the case. So this says if the absolute value of x is 6, then x had to be 6. Okay, well, absolute value of 6 is 6. That's true. So I'm just going to see if I can think of another number I could plug in here to make this true. This actually only has one counterexample. The absolute value of -6, absolute value just turns everything positive, that is also equal to 6. So the condition was the absolute value of x is 6. That means x had to be 6. There's another option here, though, because -6 would provide us with a counterexample. This last one's kind of similar. This says if x squared is 144, then x had to be 12. So in this question, if I could think of another number that if I squared it, I would get positive 144, that would be a counterexample here. And I don't know if you guys know this, but this is actually kind of similar to the question we were looking at up here. If I square 12, that is equal to 144. But there's another number that if I plugged it in for x would also satisfy that original condition. X squared, if I do -12 squared, that's also equal to 144. So this just has one counterexample, which is -12. And just real quick, we're going to sneak a definition in at the bottom of this page, and that's to write down what a converse is. So a converse is going to take your original conditional statement, and we're going to switch the hypothesis, which I'm just going to write hype, and conclusion. So from your original statement, we're going to take the if part, put it at the end of the sentence, and we're going to take the then part and put it at the beginning of the sentence, and we're going to get into that just in a second on the back. Before we do converses here really quickly, I want to give you guys some symbols. So these are logic symbols, and if you ever see this, the letter P, it's kind of in a italicized format, a lowercase letter. That always represents the hypothesis of a conditional statement, and a lowercase kind of cursive or italicized letter Q, that's going to represent the conclusion. in a conditional statement. So here's just a quick example to show you how these symbols read. And they're going to use a little arrow in this too. Okay, so here's a conditional. If an angle is a right angle, then its measure is 90. So an angle is a right angle would be the hypothesis. That would be the P part. Then I'm going to have a little arrow, and it says then its measure is 90 degrees. Its measure is 90 degrees would be your conclusion, and that would be the Q. This is read if P then Q, and that's the little arrow to indicate I go from the original hypothesis to the conclusion. Okay, now the converse, as I said on the back side of this, just flips the hypothesis and the conclusion. So the part at the end of the sentence is going to come at the beginning. This says if the measure of an angle is 90, then the angle is a right angle. So this is flipping it over, and this would go Q implies P, or if Q then P. And I don't know why I just did that. This would be a P. Let's redo that. Q arrow P. So that means from the original, the conclusion is coming at the beginning and the hypothesis is coming at the end. So we're going to practice that here. I'm just going to write the converse to these. So this says if two lines are not parallel and do not intersect. So I'm just going to underline this real quick. Two lines are parallel and do not intersect. That whole thing would be the hypothesis, and then the conclusion is then they are skew. So what we're going to do, this is your P, this is your Q. We're going to switch these. So I'm going to take this piece and put it at the beginning. So I'm going to say if, and I'm going to use part of this sentence at the beginning to just kind of make grammatical sense. But I'm going to write if two lines are skew, comma, and then I'm going to put this. Then they are not parallel, going to use that symbol again, and they don't intersect. So we're switching the hypothesis and the conclusion. So you can see this now. I'm saying two lines are skew, that would be that part. And now this conclusion, then they're not parallel and don't intersect. So from the original, this is now the Q and this is the P in opposite positions. So we're just going to try that one more time. Okay, here, in the original, if a figure is a square would be your hypothesis or your P symbolically. Then it has four sides. It has four sides is going to be your conclusion. This will be your Q. So we're just going to flip them over, but I'm going to take the word, a little word from the first part to make it make sense. So I'm going to say if a figure has four sides, then we're going to take this part. The figure is a square. And you guys can see here, this is my having four sides was my original conclusion. Now that's coming at the beginning. And my original hypothesis is coming at the end. Now we've switched the P, and this was the Q from the original here. I'm off the screen, please forgive me. All right, now we're going to slide down and do truth values real quick of a conditional and a converse. So I'm going to pause this because I'm going to run out of time. So I'm going to write down the converse for both of these statements real quick, and then we'll come back. All right, so let's start with the original statement in part A. If you need more time, go ahead and pause the video so you can jot down these or try to do them on your own. If two lines do not intersect, then they are parallel. So at the beginning here, normally we'd go through this in class, but just me today. So if two lines don't intersect, they have to be parallel. When you decide whether that's true or false, if you can think of a counterexample, that's when you would say it's false. If you can't think of a counterexample, then the statement must be true. So this says if two lines don't intersect, they have to be parallel. Okay, so I got to try to think of a situation where lines don't intersect, but they are not parallel. I'm actually going to say this is false, and my reason for that is something we learned in the first unit. Skew lines are not parallel, but also they don't intersect. So lines that don't intersect, they don't have to be parallel, they could be skew. Okay, now the converse has the initial condition, if two lines are parallel, then they don't intersect. That is true. If you have parallel lines, part of the definition is that they don't intersect. So there's no counterexample here. So the converse is actually true. And the two statements do not have to have the same truth value. They can both be true, they can both be false, and they can have one of each. It just depends on the actual statement. This is another good one here. The original statement, the conditional, says if x is equal to 2. So that's what I have to assume. Then absolute value of x equals 2. That's true. If x is 2, I can plug that in right there, and the absolute value of x would be 2. That's true. If you look at the converse, though, this is kind of like a question we had an example on the front. This says if the absolute value of x equals 2, then x had to be 2. This, if the equation is coming first, the equation actually has two answers. It could be 2 or negative 2. So this is actually false, and my counterexample would be the number negative 2. And we're going to kind of summarize down here at the end. I'm going to take this statement and we're going to put it as a conditional, and then we're going to write the converse and write the truth value of each. If we think one is false, then we'll go ahead and give a counterexample. So this is kind of a summary of everything that's gone on in this today. So this just says two skew lines do not lie in the same plane. Now there's two different ways you could write this. So if you're conditional, if you're thinking about it in a different way, might match my converse if we don't write them the same way. But technically there's a couple ways you could answer this question. I'm going to start just kind of with the beginning. I'm going to say if two lines are skew, then they do not lie in the same plane. So, in my question here, the way I worded it, my hypothesis would be two lines are skew, and my conclusion would be they do not lie in the same plane. And just while I'm here, I'm going to go ahead and write the converse. So I'm going to switch this around. So I'm going to write if two lines do not lie in the same plane, then the original hypothesis is going to become the conclusion. Then the lines are skew. And the wording on these might just be a little tiny bit different, and that's fine. We're trying to get the concept to be the same. So I'm switching the hypothesis and the conclusion of that original statement I wrote down. And now we're just going to run through real quick and see if we can answer the truth values here. So if two lines are skew, then they do not lie in the same plane. Well, that's actually part of the definition of being a skew line. There are two lines that don't intersect and they don't lie in the same plane. So if they don't lie in the same plane, there's no way they could intersect. And if they don't lie in the same plane, they couldn't be parallel. So this is actually a true statement. All right. And this converse, if two lines do not lie in the same plane, then the lines are skew. Well, if they're not in the same plane, kind of the same concept, I cannot intersect if I'm not in the same plane, and I can't be parallel if I'm not in the same plane. So both of these are actually true statements.